Okay, guys, so listen up here. This is where we left off on Friday. Yeah, I just shown you the video of the guy breaking the load of concrete. Okay, obviously the thing we have to take from that is that if you are going to do work on something as solid and heavy as concrete, right, you've got to have everything together. You've got to have those spaces in between the blocks so that the force you exert can be exerted over a distance that is greater than, well, the distance your hand would smash by breaking a similarly sized solid block of concrete. All right, having only the individual smaller blocks allows his force, okay, to only act on the first block and then go through that space before the second block, right? Thus reducing the deceleration of his hand and allowing him to break all of the blocks, okay, together. What we're going to look at today, guys, review quickly potential kinetic energy, look at a few examples of work energy theorem type questions, and then do some practice on that. Sat down yesterday and looked at where we are and where we need to be at. We're perfect. Okay, we will definitely be done this whole unit by the date of the exam that I set up there. All right, I told you it was probably going to be second week of December late or the third week. It's going to be Monday of the third week of December. That's December 17th. All right, so make sure that you've got that date put in your calendar or whatever. All right, so that you know that it is coming up 2 weeks from today. Okay. In addition to that, we will have a couple of other labs that we'll be doing. Okay, we'll be doing a work lab. We'll also be doing an energy conversion lab. We'll have the research project for this unit that we'll be working on as well within that 2 week span. Okay, so there's a few things that will be coming due for you before that exam, and one or two that'll come due after. Okay, everybody with me there? Okay. All right, so for potential energy here, okay, we said the two types of potential energy we're going to deal with most in this unit are the two types of mechanical potential energy. That is gravitational potential energy, which you have if you are where? Yeah, or above the Earth's surface. You don't necessarily have to be in the air, all right? As long as you are above the Earth's surface, you have the potential to fall, okay? The other type would be elastic, okay, like in a stretched spring, a stretched rubber band, all right? Anything that has a shape that you can change but then would have a desire to snap back to its original shape, okay, can hold and contain elastic potential energy. How do you get potential energy? What has to be done? Work. Okay, that's the key thing we have to remember here. Work energy theorem says that work is a change in energy. The only way you get gravitational potential energy, elastic potential energy, kinetic energy is if something transfers it to you. All right, everybody with me on that? All right, so potential energy then is energy due to position or condition. Okay, so a rock perched on a cliff in a Roadrunner and Wile E. Coyote cartoon, if you've ever seen that. Okay, I realize that that is now like 2 generations ago, and all right, you guys may not be as familiar with the Acme, Roadrunner trap company, right, that he would always buy his stuff from, right? But he always, at some point, resorted to putting a rock on top of a cliff and trying to push it off onto the Roadrunner, because inevitably everything he bought didn't work. All right. So the reason that it can that he would do that would be he wants to give it energy so that it can do what? Which would be, would he be changing the Roadrunner's shape were he to land the rock on him? Would that be work? Yeah, remember we said a change in shape of an object counts as work because you're at least moving some of the particles. All right? The reason he wants that rock perched on top of the cliff is because energy is the ability to do work. Okay? All right. Here's the one of the other things he tried was a big rubber band so that he could run as fast as the Roadrunner, and he would just, walk backwards with this rubber band kind of on these big posts, and then he would shoot himself forward, but he would go past the Roadrunner, and he never ever catches him. So, all right. Now, potential energy here. A couple of sort of strange applications and things that we need to understand. This diagram right here. We got a person lifting this rock to the top of this hill, and this person pushing this rock, okay, to the top of this hill. Who does more work? That's what most people would say. Most people would say that the person lifting it does the most work. In actual fact, nope. We're going to assume that that is a frictionless incline. They do the same amount of work. Okay? These two people do the same amount of work. Because at the top of that inclined plane, okay, the rock is the same height above the ground. Everybody follow me there? Regardless of how it gets there, it is the same height above the ground. What kind of energy does it have when it gets to the top of the hill? Potential energy. That can be calculated with this formula, m times g times h. Since they would both be in the same position, would they have the same amount of energy? What do you think? Would all of these variables, mass, gravity, and the height, be the same for both rocks? Yeah, I mean, in this drawing they look about the same size, so we could say that yes, they would have the same mass. G is 9.81, doesn't matter what you are, okay? And H is the same for both. So they both have the same amount of potential energy. The only way they got that energy was because somebody did work. Okay? That is the whole reason for the design of the inclined plane. It's the simplest tool. It's even more simple than the lever. Okay? The inclined plane allows you to do the same amount of work using less what? Less force, right? Okay? It becomes not about strength, but about endurance. Okay? Yes, you'll have to push this rock further to push it up the plane, but you don't have to use as much force. Because remember, work is force times distance. Everyone remember that from the other day. Okay, so this guy who lifts the rock, certainly, okay, the distance he lifts it is less because it's direct. Okay, this is the hypotenuse of the triangle here, so it's greater. He uses more force over less distance. She uses less force over more distance, but in the end, they do the same amount of work. Okay? I was actually watching a thing last night on the building of the pyramids, all the theories they have on the building of the pyramids. Almost all of them inevitably go back to gigantic ramps and millions of slaves. But, okay, gigantic ramps were generally the idea here. Okay? They had lots of sand, so lots of stuff that they could build ramps out of, and they would make these ramps that were really, really long. And then they have thousands of people pulling these gigantic slabs of sandstone up the side of the pyramid. All right? There'd be no way you could lift one of those rocks. They didn't have cranes, and they couldn't have people just, oh, all right, pick it up, and we'll walk up the side of the pyramid and put this thing where it goes. Because they were huge. Okay? They were thousands of kilograms each. So there was no way they could do it that way. So what they did is they built inclined planes, and they put these big, gigantic rocks on rollers, logs, okay, or palm trees, whatever they had. Okay? They put the big slabs on those, and then just pulled. And when one of these things got to the back, there was a couple of guys whose job was to grab the log and roll it back to the front. Okay? Everybody with me there? You can move gigantic masses as long as the incline of your ramp isn't too big and you're willing to pull it a really, really long way. All right? Does that sort of make sense? Okay? So really important to remember, guys, that the work energy theorem is the reason why a ramp works. Okay? Were it not for a ramp, all of those poor Egyptian slaves would have been inclined planes wrapped around an axis. They would be screwed. An inclined plane wrapped around an axis is a screw. Okay? Okay? That's why it's easier to put one into wood than a nail, all right? Because it's an inclined plane, and as you twist it, it uses the ramp to drill itself into the wood. Okay? Come on, it's a Big Bang Theory joke. Come on, that's funny. All right, so gravitational potential energy then can be given to an object provided it is raised in some way to a height above the ground, okay, or above something else. Now, let's look at this example over here with the pulley. Okay, what's providing the force to pull the 3-kilogram block here? Gravity. Yeah. Okay. Gravity's providing the force. What's providing the energy to do that work? the potential energy of the 5 kilogram ball. All right, and the reason it has energy is because something has done work on it and raised it above ground level. When it pulls, okay, when it starts to fall, it will pull over the pulley, okay, on this mass here. Everybody follow me there? Which one will move faster? The ball or the box? Same. Why? Exactly. They're attached. They can only accelerate at the same rate. Okay? If one were to go faster than the other, either the rope would have to break or the block would have to catch the ball. I've never seen that happen. Ever. Because it won't happen. Okay? They are moving, they're going to accelerate at the same rate. Okay? So, here's the thing. We start out, when we first lift this block up, all the energy in this system is contained here as potential energy. All right? Once this thing gets moving, what does that potential energy turn into? Kinetic energy. All right? When this is all said and done, okay, the instant before this ball hits the ground, how much energy does the system have? Yeah. It has to have the same amount as it had at the beginning when all of its energy was here. It's just now, some of that energy is where? In the block. Okay? A lot of people, they start thinking about this and they start thinking that at the end, this will have kinetic energy, like the block will have kinetic energy, the ball will have kinetic energy, and suddenly there's going to be more energy. Is that possible? No, not unless somebody pulls on the rock and adds energy by doing more work to the system. If all the energy in this system is potential energy right here at the beginning, the total energy at the end has to equal the total energy at, what's that called? The law of conservation of energy. Okay? This ball is going to do work on this ball. So as a result, its potential, or its energy, when it gets down to here, this ball's energy will not be the same here as it was here, because some of it will be used to do work on the box. The energy of the system will remain the same, because at the beginning the box has no energy. This has all the energy. But at the bottom, this thing won't be able to fall at the normal rate because it's pulling this other box. So it's going to do some work on the box. But at the end, the energy of the system will all be the same. Okay? Everybody with me there? Okay? The energy of an individual object may change during this, but the energy of the whole system is going to stay the same. Okay. So, you can calculate the gravitational potential energy of an object, okay, using this formula. And this is on your formula sheet, okay? EP equals m times g times h. Some things to keep in mind that are very important, okay? What each of these things stands for. M is the object's mass, and that has to be in kilograms. Okay? G is the acceleration due to gravity, and on Earth, that's 9.81. Units must be meters per second squared. Okay, and lastly, h is the height of the object above the ground, and that must be in meters. Okay, reason for that? A joule, okay, the unit for energy, is force times distance, right? So that's going to mean newtons times meters. Is everybody with me there? Okay, we're going to break newtons down. Kilogram meters per second squared is a newton times meters. Okay, gives you the units for a joule, which are kilogram meters squared per second squared. Okay, that's the units for a joule. Right? You can always just say joule, right? But the reason we have to make sure that these are in these units is because if they're not, we do not get joules. We would get gram meters squared per second squared, or kilogram kilometers squared per second squared. These are not a joule, okay? We want everything to come out into joules, so we have to make sure that the units we use in one of these formulas will get us to these units, kilograms, meters, and seconds. Okay, we have to have those units. All right, questions there? Is that formula going to be pretty easy to use? Yeah, I mean, it's especially nice when everything is all multiplied on one side, because if you want to isolate something, all you have to do is divide it away, right? Divide everything else away and leave whatever it is there. All right, so if I'm solving for h, I simply divide both sides by mg. Okay, so it's nice and easy to manipulate. All right, so example here, guys, and I'm just going to erase these parts here for a sec. We'll leave it. Okay, so we got a 3 kilogram box lifted upwards by lifted by an upward force 1.5 meters above the surface of the Earth to the top of a table. Right? We want to find the potential energy of the box in its new position. Anytime we want to find potential energy, we use this formula. E equals m times g times h, and we simply plug in our numbers because we don't have to manipulate this one. All right, 3 kilograms times 9.81 meters per second squared times 1.5 meters. Okay, when we do that, we should get 44.1 joules. Okay, were that box to fall off of the table, how much kinetic energy would it have the instant it hits the ground? 44.1 joules. Okay, law of conservation of energy says you can't create it, you can't destroy it, but you can convert it into other kinds. As an object falls, does it speed up? Okay, is your kinetic energy based on your speed? Yep. Okay, so as something falls, it rapidly converts potential energy into kinetic energy. All right, second example here. All right, if we're trying to find the height of a diver, okay, on a diving board, right, we would say we got a 55 kilogram diver, right, and we would write down our givens here. I'm just gonna, this one I'm gonna do this. Okay, so we would write down our givens. Mass is 55 kilograms. Okay, our gravity is always 9.81 meters per second squared. Okay, and they tell us that he has a potential energy of 5,400 joules. They're asking me to find the height of the diving board, right? So EP equals m times g times h. I want to solve for h, so I divide both sides by m times g, right? Alright, now just plug in my numbers. So h equals 5,400 divided by 55 times 9.81. Comes out to 10 meters. So he's on that the high 10-meter platform. Okay, does that make sense to everybody? Not terribly difficult, right? Okay, the reason I'm going over these formulas isn't because I don't think you can handle these formulas, but soon you're going to be in this situation where you're going to be saying that work is a change in energy, right? And you're going to have to set this equal to the change in energy, like I did in that example I showed you on Friday about slowing down in a school zone. Right? Here's the work that has to be done, all right? And then we would have m times g times h final minus m times g times h initial, and you would have to solve for one of these variables. Okay? Everybody follow me there? All right. Most of the time, this or this will be 0. Okay, one or the other of these will be 0. So you actually will just go, oh, all right, well then I'm just solving for that. And you can manipulate a little more easily. Okay, but that's where we're headed. So I just want to review how to use those formulas. All right, now this is what we talked about here on Friday with the board breaking. Obviously, it's kinetic energy that does the breaking of the boards and bricks and whatever else. Okay. So if you have potential energy and it's released, okay, an object begins to move. Right? If you're holding something and you just suddenly drop it, obviously it begins to accelerate down because of gravity, and it converts all of that potential energy into kinetic. Right? That's why you can use a hammer to drive a nail into wood, okay, and things like that. It's also why it's much easier if you're really breaking a lot of wood to use a downward motion as opposed to setting it all up horizontally and trying to punch through it. All right? Because then gravity's not working for you anymore. All right. Other types of things have kinetic energy as well, but we don't so much notice it because of the scale. Wind, for example. Okay, wind has energy. How do we know that? It does work, yeah. All right, I mean, last winter we had those 140 km/h winds that were tearing siding and shingles and even like roofs off of houses. Okay, no, down in the crescent below me, they had a house that was partially constructed, but they didn't have the windows in yet, and the wind was able to go in through the windows, and it created such a force inside that it actually lifted the roof right off of the house and set it down in the crescent. All right, it can do a lot of work because it has a lot of energy. But if you're going to have energy, you have to have mass. Where's the wind getting the mass from? What is wind moving? Air. Yeah. Does air have mass? Sure it does. Okay, it has plenty of mass. And if you get it all moving in the same direction at the same time, it can do a lot of work. Okay, right now the particles in this room are moving, but they're not all moving in the same direction. They're moving randomly, so we don't notice it. Okay, but if somebody comes up and, blows in your face, you feel that because they've now made all the particles in that area at least move in the same direction at the same time. Okay, does that make sense to everybody? All right. Okay, sound waves, similar thing. Okay, sound waves cause air particles to move back and forth. All right, those vibrations are transferred from one air molecule to the next until they get to your eardrum, and then they do work on your eardrum by making it vibrate back and forth. All right, if they're moving too much, okay, it can hurt your eardrum. It can cause damage to your hearing. It can rattle the little bones that your eardrum is attached to, and then they get scar tissue forming on them, and your hearing ability decreases. Okay, all of these are examples that they have energy because they're doing work. All right. Okay, so for kinetic energy here, guys, thing we need to realize, okay, anything that's moving has kinetic energy. Okay, and your kinetic energy is based on two things. What are they? What two things influence how much kinetic energy you have? Mass and speed. Okay, mass and speed influence your kinetic energy. And which one did we say had a bigger effect? Speed. All right, because speed has an exponential relationship with the amount of energy the object has. All right, if I double the speed, I quadruple the energy. All right, if I triple the speed, the energy is 9 times greater. All right. Okay, where on this roller coaster is the train or the cart here going to have the most kinetic energy? Cool. Here? Going down that hill, here or here? Yeah, okay. Right here it's going to have the most kinetic energy, all right? Because I shouldn't say all because it's not all anymore. Most roller coasters work on the same principle. You are towed by a lift or a conveyor to the top, all right? They give you what kind of energy at the top? Potential, right, gravitational potential energy. And then there's usually, right at the very beginning, the first hill. That's where you convert most of it into kinetic. So you'd be going the fastest at the lowest point on the ride. Okay, because that is where you have now no gravitational potential energy and all kinetic. All right, so that's where you would be moving the fastest, wherever the lowest point on the ride is. How many people have ever ridden the Mindbender at Westhead? Okay, if you have, you know that first point takes you from the highest hill on the ride to the lowest point on the ride. All right, and you are moving at over 80 kilometers an hour at the bottom of that hill, okay, and you have gotten to that point in 2 seconds. Okay, it is a very rapid acceleration. It is also a lot of fun. Okay, all right. Okay, sorry guys, formatting is just a mess here. All right, we talked about this as well on Friday, but I just want to quickly review it. Okay, thermal energy, okay, there's kinetic thermal energy and there's potential thermal energy. We're not going to deal with them very much, just as long as you understand what they are. Okay, thermal kinetic energy is the movement, how fast the particles are moving. Okay, so if you have water boiling, okay, at 100 degrees Celsius, the particles in it are moving very, very quickly. If you turn it into steam, okay, you also change its potential energy. Potential thermal energy is a measure of how far apart the particles are. So gases have the most potential energy, all right, because their particles are the furthest apart. And when they move back together, okay, they release that energy. That's why steam scalds you worse than water. All right, if you get hit by steam at 100 degrees and water at 100 degrees, the steam always burns you worse. All right, they both have the same amount of kinetic energy. Temperature is a measure of kinetic energy, kinetic thermal energy. All right, but because the steam has already changed state into a gas, it holds a lot more energy than water at 100 degrees. And so when it condenses onto your skin, it burns you much, much worse than water at 100 degrees because it actually has more total thermal energy, which is something we talk more about in the next unit. Okay, and that's as much as I want to say about that. All right, mechanically speaking, kinetic energy has to do with the mass and the speed. Okay, so the formula for that is 1/2 mv squared. What did we say the units for joules were? Kilogram meters squared per second squared. That's a joule. Well, let's make sure that this formula is in fact going to give us those units. Units for mass are kilograms. Okay, units for speed are meters per second, and it's squared. Does that give me kilogram meters squared per second squared? Yes, it does. Okay, so this works out. Okay, so things to remember again, EK is the kinetic energy in joules, M is the mass, must be in kilograms, okay? V is the velocity, must be in meters per second. Lots of questions will try to catch you here. They will give you a speed in kilometers per hour. Okay? You cannot use kilometers per hour in an energy calculation. Because it's actually using an average, okay, in case there was a change. Yeah. All right. So we gotta have, like we said, gotta have the speed in meters per second. All right, has to be that way. And then lastly, guys, make sure that we get our joules there at the end. So kilogram meters squared per second squared. Okay, we're gonna skip those. Okay, because those are all thermal things. What I want to do here, guys, is just do a couple of these questions here with you. Then I'll give you this worksheet in just a second. All right. Actually, you know what? I'm just going to make up a couple of examples. That'll be better. Okay, write this example down, guys. Okay, so we have this 150 Newton force applied to a rubber band stretching at 15 centimeters. We want to find out how much elastic potential energy is present. What do newtons measure? Force. Anytime you see newtons, you are dealing with a force. Okay, so writing down our givens, the force in this question is 150 newtons. And it says it stretches at 15 centimeters. Okay, I'm trying to find potential energy. What can I assume the initial potential energy of the rubber band was? 0. Okay? If you're not told otherwise, you can assume it was 0, unless they told you its initial length was something. Okay? Maybe it had already been stretched 5 centimeters or something like that. Okay? In this case, we're going to assume it was not stretched at all. Okay? How can I calculate this then? What will these two things let me find? Work. Okay. Okay? And what does work equal besides force times distance? Yeah, a change. The change in energy. All right? So I can say then that force times distance equals the change in the elastic potential energy of the rubber band. And we just finished saying that we can assume, since we weren't told otherwise, that the initial potential energy of the rubber band was 0. All right. So can I say then that the force times distance equals the potential energy now in the rubber band? Yes. Okay, so 150 times 0.15, because I have to convert it to meters, okay, will give me that. Okay, so 150 times 0.15 is 22.5. Okay. Okay. Okay, 22.5 joules. Is that fairly straightforward? Okay. Okay, let's try another one here. This one will be a little trickier. Okay. This would be very much like what I would ask on a quiz or a unit exam for a work energy theorem type question. Okay, what am I given? Okay, I'm given a distance, 100 meters. What else am I given? Mass. And force. Okay, 16,500 newtons. What am I asked to find? Speed. In particular, I'm asked to find the final speed, because I'm told it's initially not moving. Okay. So they're telling me this force is making the car go faster in the question. These are the things I have to read into the question. It doesn't outright say this is making the car go faster, but it's saying it was initially at rest, now how fast is it going? Okay? What kind of energy is this force changing? It's changing the kinetic energy. All right? These are the things we have to be able to read into a question. See why physics can be tricky? Okay? The math is easy, but it's being able to see what's going on in a question. All right? We're changing the kinetic energy of this car because we're making it go faster. All right? So that means that work is, again, a change in energy. Okay? And in this case, it's a change in kinetic energy. Formula for work, force times distance. What's the formula for kinetic energy? One half mv squared. Okay, that's the formula for energy. Everybody follow me there? Okay. Now, I'm changing the energy. That means final minus initial, yes? Okay, so final minus 1/2 mvi squared. Okay to say that. Can I simplify that right now? What can I take off? Right, I can take off the initial kinetic energy because it says right in the question it was initially at rest, which means it initially had no kinetic energy. All right, can I solve for VF? Yeah, because I have mass, I have force, and I have distance. Okay, so I divide both sides by 1/2 of m. And I'm looking for VF, not VF squared, so what should I do? If I have a squared number, how do I get it not squared? Right, square root it. Okay, if I square root both sides, I'm left with just VF. Making sense, guys? Okay, so if we plug in our numbers here then, okay, is this pretty much what I showed you with the example of the car in the playground zone? It is. Okay, except that on that question we tried to solve for distance instead. All right, now we're solving for V. All right, so we plug in our numbers, 16,500 newtons times 100 meters over 1/2 times 1,500. Okay. Okay, so the car is now traveling 46.9 meters per second. Okay, is that all right with everybody? All right, do one more here. And this is going to go. This example is going to go over something that they'll try and catch you with once in a while on a worksheet. Okay. Okay, so we have this object whose weight is 190 newtons. It is subjected to 900 joules of work. It's lifted vertically, let's say off the ground, so that we know that initially it's at ground level. Okay, how high is it above the ground after the work is done? Okay, mass and weight, are they the same thing? No, they're not. Okay, your mass is a measure of how much matter you are made up of. It never changes. Well, unless you actually go on a diet and lose mass. Okay, if there's actually less of you, then you have less mass. Okay, your weight is the force of gravity pulling on your mass. All right, that can change. Okay, if you go to the moon, you have exactly the same mass, but you weigh less. because the force of gravity there is smaller. Okay? The moon is smaller. It doesn't pull on you as hard. You don't accelerate towards it at the same rate you do on Earth. In fact, you would weigh 1/6 of what you weigh here. All right? Even though there'd be just as much of you, the same mass as there is on Earth. Okay? Mass is always measured in kilograms. But because weight is a force, it's measured in newtons. Okay? So when they give you your weight, or an object's weight, they are giving you the force of gravity, which can be calculated by doing this. Okay? M times G. That's actually on your formula sheet. All right? It's not something we use very often, but it's important to know what it is. All right? Have we seen these two things together in a formula already? Yeah, M times G times H, which gives us potential energy, right? So if this is a force, and I multiply it by H, is that force times distance? Sure it is. Okay? When you calculate the gravitational potential energy of something, you're calculating the force of gravity acting over a distance, okay, or vertical height. Everyone follow me there? Okay. So in this question, they've already given me M times G, haven't they? Okay, everyone follow me on that. All right, so they gave me work. They told me it's 900 joules. Okay, they gave me force. Okay, the force of gravity. They told me it's 190 newtons. All right, I'm trying to find what? The height. Okay, well, work is force times distance, which is the same as saying M times G times H. Can I find H? Yeah, because I know that this is 900 joules, and I know that M times G is 190. All right, so here's what I'm going to do. Work equals M times G times H, and I'm going to divide both sides by mg, and I'm going to leave H over there, since I know what mg equals. All right? The other way we could do this is we could just say, this is the force, and the height is the distance, and I'm going to divide the force over. Mathematically, it's the same thing. All right? So here's what we're left with. 900 joules divided by 190 newtons, okay, will give me the height of the object. So 4.7 meters, we'll say. Okay, so now you've got a few examples. Okay, essentially all the work energy theorem questions will break down to something like that. Most of the questions we work on today will be a little easier than that, right? They'll simply be, you know, force times distance and things like that. All right. Had a number of people coming and asking about number 3, so I'm just going to quickly go through number 3. Okay, so we got this person standing on the gym floor, and they jump straight up to dunk a basketball. Right? They have a mass of 70 kilograms. All right, so mass of 70 kilograms. They have 800 joules of potential energy. If we're going to assume this gym is on Earth, where all gyms as we know it are located, G would be what? 9.81. That's the thing they don't tell you in the question, and they don't have to tell you. You just assume. All right. Anytime we're dealing with a change in height, we're dealing with 9.81 meters per second squared in some way. All right. So what they've given me is EP. EP equals M times G times H. Does everyone follow me there? Which you could have also, and a few people are doing this, they're going, work is equal to energy, and that's force times distance. And that's fine too, and then they're going M times G to get the force. Well, that's the same as doing this. Does everybody follow me? I just think it's easier to use this one rather than get confused with changing variables. All right? So if I want to solve for H, here's what I have to do. H is going to be our 900 joules divided by 70 times 9.81. And here's the trick. That's got to be done in brackets. If it isn't, it will not, oh sorry, 800 joules. It will not come out right. All right? The bottom has to be brought over as one piece. work is a transfer of energy. He does work on the floor does work on him, giving him 800 joules of potential energy. Yeah? Does that make sense? Okay? I don't want you to think work and energy are the same thing. They're not. But the only way he gets this 800 joules of energy is because he does work. Right? He pushes against the floor. And the floor pushes back. Yes? When he is at this height, okay? When he's at that height, he has 800 joules of energy, right? Now, while he's moving, he still has 800 joules of mechanical energy, some of it potential, some of it kinetic, but we don't know how much at those points. All we know is that the energy he has at this height is equal to the work he had to do to get there, just like we did with the block moving up the ramp. Okay, is everyone following me there? That's the real tricky part to physics, guys, is being able to see through a question. All right? Any other ones giving us trouble while I'm up? Okay. It all becomes very chicken egg kind of stuff, yeah. All right, number 6. All right, so we have a rubber band that has a mass of 0.02 kilograms. Okay, it has 320 joules of kinetic energy. How fast is the rubber band going? Okay, so here's what I have. I know that EK is 320 joules. I know the mass is 0.02 kilograms. I'm looking for V. Okay, EK equals 1/2 mv squared. How do I get V by itself? Right, divide by 1/2 of m, and then what? I have to square root because V is squared. All right, so V then is going to equal the square root of 320 joules, okay, divided by 1/2 times 0.02. Okay. So right, that's 1/2 of 0.02. 179 meters per second. Now you know why your parents told you, don't fool around with that rubber band, someone will lose an eye. At 178 meters per second, yeah, that'll take out somebody's eye. Okay? No, sorry, multiply by 3.6. That's a pretty fast rubber band. You wouldn't want to get in the way of that. All right? But you know what, guys? Like, realistically, when you put a rock in a slingshot, you can get it moving pretty fast. Okay? Like, rubber bands can store a lot of energy. Okay, listen up here, guys, real quick. Tomorrow's quiz. Tomorrow's quiz will have 1 acceleration question and 1 work question. Okay? Did you say, all right, girl? Oh, okay, good, because otherwise I would have been a little embarrassed. Okay, so make sure, guys, you're ready for those 2 types of questions. Okay, I will post that quiz on Twitter later on today.